Hello. I just wanted to get us started on the next section in our textbook, but before I did that, I just want to kind of give you a little bit of a direction where we're headed. So we've already done some basic integration, and I've told you that the reason that we are going to do integration is because it helps us find the area under the curve. So for example, if I give you a function like this, and I say find the area under the curve that's bounded on the left by the y-axis, on the bottom by the x-axis, and then just where it kind of intercepts there. So I would ask you to find the area under the curve right here. Right, that's what we're going to do with integration. So this next section that we're talking about is called area, but it is not going to let us do that in our shortcut way. But we're going to be building up to that. So you might be wondering, as we're doing the stuff that's coming up in this section, how the heck does it relate to area? Because it's going to be all sigma notation. Again, some of you may have seen this before, others this will be the first time, so we'll talk about that first. But if you remember when we did derivatives, how we just did baby steps, baby steps, baby steps, and that's kind of what we're doing here. Sigma notation is going to ask us to add a bunch of things up that follow a certain pattern, right? So, and then we'll use that to find a sum. So imagine what we're going to do here is we're going to find the area of, let's say, this rectangle right here. And then we might find the area of this rectangle, and then the area of this rectangle. I'm drawing this wrong, just so you know. And then the area of this rectangle, and so forth, until we get an approximate area for the area under the curve. And then what we'll do is we'll get better and better and better by, let's say, making the rectangles smaller, right? So now there's less scrap as we do this. And so in order to do that, we need to come up with a sum that we're going to add up of all these little areas. And that is what this section is going to do. So as we start to do this, and you wonder why our focus maybe is on this sigma notation, it's just so that we can start adding the patterns that come up from, say, a function like this, whatever the formula is for our f of x, that we would continue to add things that are relative to this and follow a pattern. So as we do this, don't think that we're just going off in a really random tangent here. There is a reason for it. So for starters, I hope that you will get out your 4.2 notes, which you should already have. If you've misplaced them, I've linked them onto my school. So again, this section begins by introducing a concise notation for sums. The notation is called sigma notation because it uses the uppercase Greek letter sigma, and it's written like this right here, right? And in sigma notation, the sum of the n terms a sub 1, a sub 2, a sub 3, a sub 4, etc., all the way up to a sub n is written as this. Again, this notation is called sigma. For some reason, my computer will not let me do it the proper way. The proper way is to have the I at the bottom and the N up at the top. That's the way you'll see it in the textbook. I've tried and tried. I can't get my computer to do it properly. But we would read this summation or sigma I equals 1 to n. I is called an index. It's like the subscript down here, and it's just counting whatever term it is that we're adding up. All right, so when we let I go from 1 to n, as it does here, that I, the subscript there, is what's changing, and it's telling us it's changing from 1 up to n, just as it did here. It went from 1 all the way up to n. A sub 1 stands for the first term. We don't know what it is, but that is the way we note it, that it is the first term, right? A sub 1, and A sub 2, and A sub 3, and so forth, all the way up to A sub n. I is called the index of summation, and then A sub I is the ith term, that sounds weird, of the sum, and the upper and lower bounds of summation are 1 and n. So the lowest subscript, or the lowest index that we use, the number in the index there is 1, and the highest is n. All right? So This is the index of summation. The I is 1 and n. Those are the upper and lower bounds. That's the lowest index we're going to use. That's the highest we're going to use. And then it's telling us to add all these terms. Now, we're going to get some more of a pattern here than just saying, just add, you know, these terms together. There will be patterns here. So we'll look at that in just a second. All right, note the upper and lower bounds must be constant with respect to the index of summation. However, the lower bound doesn't have to be 1. Any integer less than or equal to the upper bound is legitimate. So sometimes what we'll see is instead I don't want to add up all the first n terms. Maybe I only want to add up from 5 to n. So then of a sub I. And what that would look like is I want to add up a sub 5 plus a sub 6 plus a sub 7 and so forth until I get up to a sub n. So we don't have to start at 1 here. It could be some other number. All right. Okay, so let's take a look at some of these examples and notice how here we're starting to get a little bit more specific and just instead of just being really general and just saying a sub 1, a sub 2. So here it's telling us, again, sorry about the weird notation. I'll just write it the way it should be. We're adding up the first 6 terms, and the way the terms are defined is just by I. All right. And so what we're going to do is we're going to roll through all these I values that we have, 1, 2, 3, 4, 5, and 6. And we're going to do what it says and add them all together. All right. So in this case, when I put 1 in here, I just get 1. So it's telling me to add up, the first thing is 1. The second thing is when I put 2 in here, because again, we're scrolling through all these I values. When I put 2 in here, I just get 2. Then I do it again. I move the counter up. Now we've finished with 1 and 2. Now we're going to do 3. So I get 3. And then we do 4. And then 5 and 6. And we stop at 6 because it told us to stop at 6. It didn't want us to go past that. If this were, let's say, 10, then we would keep going until we got up to 10. All right. So there's 2 parts to this. One is that we could just say, hey, this is what this means. All right. And so it's just asking us to add up the numbers from 1 through 6. And the second part would be, well, what is the sum? All right. And that is going to come more in a little bit. But since this one's easy enough, let me just do this one. All right, so if we add them up, I would say that 1 and 6 is 7, 2 and 5 is 7, 3 and 4 is 7, that's 3 7, so this would be 21. Again, we're not going to do that for all of them because they're going to get really difficult and we don't have the formulas yet, but part of it is just recognizing what this means, and then the next part is going to be adding them up. All right, and for right now, we're going to focus on this. Okay, part B, all right? Here, again, notice that the lower bound here it changed to 0, and the upper one changed to from 6 to 5. And also, the way we're adding things together, or what we're adding together, are changing. So again, I'm going to write this the more proper way. I equals 0 to 5. And it's telling us to take whatever I value we have and plug it in here to find out what that term is. So this would be that index of 0 would indicate that our first term that we're adding is a sub 0. But what is a sub 0? Well, that means plug in 0 in for I. We get 0 plus 1, which is 1. So a sub 0 is 1. All right. When I is 2, I'm sorry, when I is 1, that's a sub 1, the first term. So we plug it in here, we get 1 plus 1 is 2. When I is 2, we get a sub 2, the second term. Or, I'm sorry, a sub 2, yeah. It's not really the second term, I guess. It's the third term because we started with 0. But then we would do 2 plus 1 is 3. Right, hopefully you can see what's happening here. We're getting exactly the same thing here because they've just changed this a little bit so that it works out to be identical. But if we do a sub 3, right, we put in 3 here. 3 plus 1 is 4, so that's a sub 3. We're going to keep doing that 2 more times. Oops. When I do a sub 4, right, I plug in 4 here and I get 5. And when I do a sub 5, I plug in 5 here, I get 5 plus 1 is 6. Right? So what we're showing here is that there's more than one way to add up the numbers 1, 2, 3, 4, 5, 6. There's more than one way to indicate that in sigma notation. So we could just do the very basic, just add up 1 to 6. All right, so we just have our counter go from 1 to 6, and we have our, the description of the terms that we're adding up just be, just plain old I. If all I want to do is add up the first 6 things, and I just write, I'm just going to keep adding up the numbers as they change. But here I'm kind of messing things up a little bit just so that you can see that you can change it around and still get the same thing. So if I decrease my lower bound on my index to 0, and I decrease my upper one to 5, but then when I go in here and I say, no, always do one more than what I is, then I will end up getting that same thing. Okay, part C. Again, let me rewrite this. J equals 3 to 7. That index doesn't always have to be called I. We'll see that we change it around sometimes. But it usually is either I, J, or K. All right, 7. And then it's telling us to do J squared. All right, so we're going to have a sub 3. Again, that's our index right there. We're going to have an a sub 4. We're going to have an a sub 5, an a sub 6, and an a sub 7. All right, and again, I went from 3 to 7 because that's what the index did right here. So now to figure out what those terms actually are, I'm going to plug in those different values, the 3 up through 7, to find out what this is. All right, so when I plug in 3 for J, I get 3 squared, which is 9. When I plug in 4 for J, because again, this is a sub 4, our fourth, when our index is 4, then we get 4 squared, which is 16. When I do it for 5, I get 5 squared is 25. When I do it for 6, I get 36. And when I do it for 7, I get 49. Right, and again, right now we're just really focusing on making sure that you understand what this means, but eventually we'll talk about how to come up with the sum of those 5 terms. Okay, let's do this one right here. This one's going to be a little bit weirder. And again, I'm just going to rewrite this as k equals 1 to n of 1 over n times k squared plus 1. All right. So many weird things about this. First of all, that we don't stop at a number, we stop at n. And the reason for that is because sometimes we just want to know what this looks like in general, so that we could really come up with a formula and then change it into anything we wanted. So let's just go through and write this out. Again, the weird thing is going to be we don't know where to stop, so I'm just going to write this is going to be a sub 1. We'll just do a few of these, and then we'll generalize what it's going to look like. So a sub 1, a sub 2, a sub 3, and then let's do dot, 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 and then a sub n. All right. So when k, which is our index, when k is 1, let's think about what we would get here. All right, so I would plug 1 in here. 1 squared gives me 1, plus 1 is 2, times the 1 over n. I'm just going to write it right now just so that it'll make it a little easier when we get to this one. I'm just going to write it as 1 over n times 1 squared plus 1. All right, again, as we get better at these, we're going to see how this plays out a little bit more. But for right now, we're just substituting things in. So for a sub 2, this is going to change to 1 over n plus, or times 2 squared plus 1. Right, when we get to a sub 3, this is 1 over n times 3 squared plus 1. Right, so what do you think this one's going to look like? Right, hopefully you're saying that it's going to be 1 over n plus n squared, or I'm sorry, I keep saying plus, times n squared plus 1. And again, for right now, don't touch that. There's really not a whole lot that we can do that's going to make that better with what we know. But for right now, that is the way that you would write out the first n terms of this sequence. And again, here n is acting as somewhat of a constant because it's not changing. It's the k that's changing, right? So only the k is really the variable, and n is just some fixed number that we don't know. Okay, last one here. Again, I'm going to write this with the more normal way. I equals 1 to n again. So we're ending up here as our upper bound is n. And then it says f of x sub I times delta x. Right? You're familiar with delta x. We've used that in a lot of different situations throughout the year. And I know you've used it in science too. But this is kind of weird. All right? So here our subscript is... we're not really plugging it into some formula like we did here. We're just changing the index down here. So this, again, if we're going from 1, so this is a sub 1, and then a sub 2, and then a sub 3, and then something, and then this is going to be a sub n, our last term right here. All right, so when we put in 1 in here, this is just going to tell us f of x sub 1 times delta x. Completely unsatisfying, but again, this is hugely applicable as we're getting ready to do finding the areas. This x sub 1 is going to be the end point of our first interval. Again, if you think back to what I just said right here, this might be an x sub 1 right here. Right, the end point of one of our intervals. So f of x sub 1 would tell us this value right here. All right, and then delta x is going to be something like this, the width of that. So if we do f of x sub 1 times delta x, that's going to tell us the area of this curve, or the area of this rectangle. Right, so weird as this looks, it's actually going to be hugely helpful in a little bit. All right, same thing here. We put in 2. This is going to say f of x sub 2 times delta x. Right, then we go on and we plug in 3. So this is f of x sub 3 times delta x. And then dot, 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 we would keep going until we get to f of x sub n times delta x. Right? So again, right here I just am hoping to familiarize you with, how we read these, and again, we'll get to how to do them in a little bit. So then let's look at the part down here. So these are just going to give us some properties. These are hopefully going to be pretty obvious to you after what we've just done up here, but the next few will be more significant. All right, so this is saying if we have some constant in front of our term, that we could just pull it out. And we actually, that might be obvious looking at this one. Remember here, this was kind of a constant right here. And if we added all these up, notice that we could just factor that 1 over n out of each of them and ignore it, and then just worry about this part of it. That's exactly what that's saying. It's saying if there is some sort of constant in front of our term, we can pull it out front and just focus on adding up those terms, and in the end, multiply by the constant. All right. The second part is saying if we're taking the sum of 2 separate things that are either added or subtracted, that we could break it apart. I guess you could think about this one maybe doing this. This is like 1 plus 1. I'm sorry, 0 plus 1. This was 1 plus 1. This was 2 plus 1. This was 3 plus 1, and so forth, that we could just really add up the 0, 1, 2, 3, 4, 5, and so forth. The first part, like this, and get a total, and then add up all these second parts, the 1, the 1, the 1, the 1. So it's telling us that if we have 2 things that are added together or subtracted from each other, that we could really just break them apart into 2 separate ones if that makes things easier for us, and it usually will. Right. These, though, are the more significant ones that we're going to use frequently. And again, you're just going to have to memorize them. I don't think it's going to be hard because you're going to use them so much that that they will just start coming naturally. So here this is saying if we are summing up a constant, then it's just, the sum is just the constant times however many times we added it up. So let's say, for example, we did sigma I equals 1 to 4 of 3. It's telling us that we want us to add 3 together 4 times. All right, so our first term, a sub 1, is 3. Our second term, a sub 2, is 3. Our third term, a sub 3, is 3. And our fourth term, a sub 3, is 3. It's just that constant times however many times we added it together. All right, so we would just do 3, the constant, times 4, however many times we did it, and that would give us 12. All right, so it's the constant that we're adding together and the number of times that we added it up. This one says that if we're adding together, this is just like that first one that we did, I equals 1 to n of just I. If we're just adding a string of consecutive numbers, then the way we do that is we take whatever the highest one is. So let's do back what we did for the I equals 1 to 6 of I. All right, so it's saying take the highest number, which is 6, times one more than that, so 6 plus 1, and divide it by 2. All right, so 6 times 6 plus 1, which is 7, so 6 times 7 is 42, divided by 2 is 21. That's exactly what we got when we did the first problem like that. This is a cool thing. I don't know if you've ever, during your course of this year, as you've been doing some puzzle problems, if you have found this formula. But this was our good friend Fred Gauss came up with this when he was just a boy, because his headmaster was annoyed by the boys in the class and really just wanted to keep them occupied. And so he had them add the first 100 numbers together. So he had to find 1 plus 2 plus 3 plus all the way up to 100. I'm just going to go up to 10. But Fred Gauss, or Carl Friedrich Gauss, was finished in minutes, and the headmaster was like, I think that you're wrong. You can't possibly have gotten it that quickly. And he had it right. And so what he noticed was that each time he added a pair, which again is why I'm just going up to 10, but they all came up with that constant sum of 11. So 1 and 10 is 11, 2 and 9 is 11, 3 and 8 is 11, and so forth. So this this 1 plus 10 right here gives us an 11. That's the 1 plus 6. And if you remember when I did that first side, we kept getting a 7. And so it's adding, it's making that pair, that sum, and that is what that is. And then this part right here is going to tell us how many of them we have. All right, so in this case, it would be 5 of them. 1 and 10, 2 and 9, 3 and 8, 4 and 7, and 5. All right, so we would end up with, no, that doesn't quite work that way. This is one that, it still does work. I just can't explain it as easily as I could there. No, I just made a mistake there somewhere. It definitely still works. But anyway, that's how we get that 21, or just that's how this formula comes into being. All right, these two you're going to find much more annoying as we need to use them. But again, if we're finding the sum of the squares, then it's n times n plus 1 times 2n plus 1 over 6. And then here is the sum of adding up the cubes. All right, so let's just go through here and do example 2. So it's asking us to evaluate this. It's asking us to find the sum of the first n terms when this is what we're adding up. All right, so it's asking us to do this 4 times. Once when n is 10, once when it's 100, once when it's 1,000, and once when it's 10,000. So for right now, we're just going to leave n in place, and then we're going to come up with a formula that we can use for each of these 4 things right here. All right, so we're going to have I equals 1 to n of I plus 1 over n squared. All right, so we're just going to use these 5 formulas that we just, I'm sorry, 6 formulas, the 4 here and the 2 on the bottom of the other page. All right, so I'm going to rewrite this as I equals 1 to n. I'm just going to rewrite this as 1 over n squared times I plus 1. Again, n looks like a variable, but it is a constant because at some point it's going to be 10. We're going to do it again and it's going to be 100, then it's going to be 1,000, then it's going to be 10,000. But within the problem, it's going to stay a fixed number. All right, so when we change it to 10, it's always going to be 10. It's not going to be an unknown. So I'm going to break this apart because now this is a constant. All right, and again, this is like this one right here. Now we've got a constant in front of it. I can just pull it out. So I can rewrite this as 1 over n squared times the sum I equals 1 to n of I plus 1. All right, again, now I'm going to use this one and I'm going to break it up into two separate ones. So in our case right here, this A is I, and then this B is 1. Right? So when I break that up, I'm going to get 1 over n squared, and I'm going to write this as summation I equals 1 to n of I plus summation I equals 1 to n of 1. All right, so I'm just taking and I'm breaking that apart. Again, be careful here because we definitely need brackets around this because this 1 over n squared is going to get multiplied through to everything. All right. Now let's go back up here because now we have this, right? So we've got I equals 1 to n of I. I can just replace this now with this, right? So I still have my 1 over n squared, and then I'm going to have n times n plus 1 over 2 plus, right, this one is back to here where I just am summing up a constant, right? And our constant in this case happens to be 1, right? And so what this formula tells me to do is just take the constant times the upper bound up here. So in this case, the constant is 1 and the upper bound is n. So this is 1 times n. All right, let's just clean this up a little bit here now. I'm going to change this so that it has a common denominator of 2. So we end up with 1 over n squared. And then I'm going to also multiply this out. So n squared plus n over 2 plus 2n over 2. And when I combine like terms here, then I end up with 1 over n squared times n squared plus 3n over 2. And then when I distribute this through here, I can actually cancel out, there's a common n in both of these terms. So when I cancel that out with this n down here, I end up with a final of n plus 3 over 2n. Okay, hopefully you're feeling okay with that. Again, just a recap that I'm treating this as a constant because n is going to be some constant number as we go through and do this. So I can just pull this out front. Then I can break this apart into two separate sums, and then I just use these two formulas right here to fill in, and then the rest is just algebra here where we're simplifying. All right, so now let's go through this. We're going to do it 4 times. So when n equals 10, right, then we just plug 10 in here. So we get 10 plus 3 is 13 over 2 times 10. So we would get the sum is 13 over 20, which is approximately, actually it's not approximately, it is equal to 0.65. All right, when n equals 100, the sum is 103 over 200. Right, and that is not approximately, it is actually equal to 0.515. And then we would do it again when n equals 1,000. Right, hopefully you see what's happening here. 1,000 plus 3 over 2,000, so 1,003 over 2,000. which ends up being 0.5015. And finally, when n is 10,000, the sum is, right, we put the 10,000 in here, the 10,000 in here, so we get 10,003 over 20,000. Yeah, 20,000, and that is 0.50015. Right, hopefully you can see a pattern here that's going on, and think back to when we did limits back in chapter 1. We were doing limits in terms of finding the derivative, but here we could find the limit of this sum as we keep letting the number of terms get higher and higher and higher. And then this denominator is going to get bigger and bigger and bigger as we keep going through. So we're going to say that as n approaches infinity, right, then the limit of this sum, limit as n approaches infinity of sigma I equals 1 to n of I plus 1 over n squared, we're going to say that that is 1/2. Well, and I'm just going to replace this with, hold on, I'm running out of room here. The limit as n approaches infinity, I'm going to replace this with this that we got. So this is n plus 3 over 2n. All right, from our work in section 3.5, I think, where we did limits at infinity, we know that if we have a rational function like this, whose highest exponents match, right? So here the highest exponent is 1, in the denominator it's 1, that it's just the ratio of the leading coefficients. So here the coefficient of the n is 1, here it's 2, so this limit is 1/2. And we can see that as we keep letting n increase, that this sum is getting closer and closer and closer to 1/2. Okay, let's take a look at an example 3. So I want you to, again, see where this is headed. So we're going to approximate the area of a plane region. Again, plane just means two-dimensional, because there are ways that we can use this to find the volume of a three-dimensional solid. We're just going to kind of spin it around and around and make a 3D shape. But for right now, we're just going to work on a plane region. Use the 5 rectangles in figure 4.9a, and on the next page it's going to be 4.9b, to find two approximations of the area of the region that's lying between the graph of f of x equals negative x squared plus 5, right? So this is the graph, negative x squared plus 5. It's a quadratic, it's upside down, and it has its vertex at 5. So we want it to be, the boundaries are negative x squared plus 5, the x-axis down here, so that's as low as we're going to go, x equals 0, that's the y-axis right here, and then x equals 2. Again, notice we could continue this on to make it look more like a parabola, but we're just going to chop it off right here. Right? So they want us to find the area of these 5 rectangles to come up with an approximation for the area under the curve. Now before we do that, I just want you to note or ask you, will the area that we come up with, the area of these 5 rectangles, be more than what the actual area is or less than what the actual area is? All right, so hopefully you're going to say it's less than what the actual area is, because if I'm finding the area of these 5 rectangles, right here, notice that there's all this area here which I don't even account for, all right? So the true area of this region that we've bounded in here is going to be bigger by all these little segments I've shaded in, all right, that we can't count because of the rectangles that we've chosen. We've all chosen ones that are underneath the curve, all right, so that they're going to be too small. So what we're going to get in this first one is an under approximation of the area of the curve. And when we get to the next page, which you can look at really quick, you'll see that we're going to get an overestimate because we've counted spaces here that aren't actually, sorry, I don't even know if you can see this. We're counting areas that aren't even actually under the curve. So we're going to do this 2 times, once for this one that's too small, once for this one that's too big, and then we'll conclude that the actual area is somewhere in between them. All right, so let's take a look here. So we need to say what the intervals are. So they've noted down here that we go from 0 to 2/5, 2/5 to 4/5, 4/5 to 6/5, 6/5 to 8/5, and 8/5 to 10/5, which is 2. And again, that's where we're stopping right there. All right, so the first thing we're going to say is our intervals are just what I just said. I'm just going to write them down. So 0 to 2/5, and then 2/5 to 4/5. Sorry, my desk space is getting a little messy here. 4/5 to 6/5, 6/5 to 8/5, and 8/5 to 10/5. All right. Now, we need to find out, well, let's first note that the width of each of these is constant. All right. So hopefully you're realizing that the width of each of them is 2/5. So when we go to find the area of each rectangle here, we're going to have to take the width, which is 2/5, and find the height of it. Now, if we look, the height of it is right up here. We want to find out where that height intersects the curve, because that is going to tell us what the value is that gives us that height. So notice that it doesn't actually hit the curve over on the left end point, it just hits some value lower than it, but on the right end point it is exactly on the curve. All right, same thing here. The second rectangle's height is exactly the same height as the value of the curve right here at x equals 4/5, and so forth. All right, see that? This left endpoint right here is not helpful to us because it doesn't intersect the curve, but the right one is going to tell us the exact height at that point, all right, because it is touching the curve. Same thing right here, right here. All right, so as we go through here, what we're going to have to do is find out what the height is at each point. All right, so we're going to have to find out what the height is at 2/5, what the height is at 4/5, what the height is at 6/5, 8/5, and 10/5, and that's going to give us the height of this box so that we can find the area of this, and this, and this, and this, and this. Now, this is small enough that we could do by hand just by plugging in these different values, but we're going to use this as a way to practice for when we need maybe not 5 rectangles, but 100 rectangles. So we want to come up with a pattern that's going to describe how we're doing this so that we can get practice with it while we're doing just something really tiny like this. All right, so we need to evaluate F, evaluate F at the right endpoints of the intervals. It's not always going to be the right endpoint. In the next example, or in part B, we're going to do the left intervals. It's also the right intervals right now because this is decreasing. If the function's increasing, that could change. So don't assume that it's always going to be the right endpoints, but we do need to take note of what it is each time, whether we're going to use the left or the right. And in this case, it's going to be the right endpoints. All right. So the first thing we need to do is we need to indicate what we're adding up. All right, so first of all, we're going to add up 5 things. So this is going to be I equals 1 to 5. And then we need to have 2 things here because, again, we're adding up the areas of the 5 rectangles. So this part has to indicate the area of each one so that when we will add it up 5 times. So this is going to have to be the height. and this is going to have to be the width. Right? So that this collectively is going to give us the area. And again, it's the area of the first rectangle when I is 1. It's going to be the area of the second rectangle when I is 2, the area of the third, and so forth. All right, so we're going to get 5 different areas that will add up. All right, so let's go through and do this. The width is the easy one because that's just a fixed 2/5. So for right here, we're just going to put 2/5. The height is going to be the value of the function, again, this function that we're talking about right here, which is negative x squared plus 5. So it's the value of the function at a specific point. All right, well now let's describe what that point is. So this first one is 2/5. All right, so we would have to do f of 2/5, then f of 4/5, then f of 6/5, f of 8/5, f of 10/5. How could we get that value to change? Like what expression could we do so that when we keep changing I from 1 to 5, we get the numbers 2/5, 4/5, 6/5, and so forth. So let's see, when I is 1, we want to get out 2/5. All right, well let's see, this is 2/5. Sorry, I'm just doing my scrap work here just so that you can see it. I know what it is, but I want you to see my thought process here. This is actually 2 times 2/5. This is 3 times 2/5. I should go back. This is 1 times 2/5. Oh, I see it now here. This is the value of I. I is 1, I is 2, I is 3, and each time it's that 2/5 that stays the same. All right, so if we were to write that as a variable expression, this would be 2 times I over 5. All right, that is the endpoint that we want to put in each time, and that is what it will change to as we increase I from 1 up to 5. All right, so if I put in 1 here, I get f of 2/5, and that's going to give me the height of the first rectangle. If I put in 2 here, I'm going to get 2 times 2 is 4 over 5, which is 4/5, which is the second endpoint. So that's going to give me the height of this second rectangle and so forth. All right. Hopefully you're feeling okay, because I would say that's a big step right there that we needed to do. All right, let's keep going. All right, so then this, now I'm going to replace this f of 2I over 5 with the value that I get when I plug it into negative x squared plus 5. So I'm going to get sigma I equals 1 to 5. And when I plug 2I over 5 into this, I get negative 2I over 5 squared plus 5 times 2/5. All right, so I just took this f of 2I over 5, I plugged 2I over 5 in here, and I got this. All right, this part is going to be really not enough room to do this. My apologies for that. So let me just do this on a separate sheet of paper. Okay, so you're probably going to need another piece of paper for this, and I'm really sorry that the notes don't leave enough room. All right, so let me write where we are here. So I equals 1 to 5 of negative 2I over 5 squared plus 5 times 2/5. All right, so we need to add that up, whatever that is. All right, so again, this is the height and the width of each of those 5 rectangles in our picture. Again, this is not it right now. So let's just break this up and see what we get. All right, so first of all, I notice that this constant is being multiplied by this, so I'm going to use that property that we have that says I can pull this out front. So I'm just going to have this as 2/5 sigma I equals 1 to 5 of negative 2I over 5 squared plus 5. I also have 2 things added together here, which I'm going to rewrite then as 2/5. Sorry, the light is glaring on here. I hope it's not too bad of a hope you can see it all right. I equals 1 to 5 of negative 2I over 5 squared plus summation I equals 1 to 5 of 5. All right, again, that part's going to be easy. Let's just kind of clean this up a little bit. You can do these steps in different orders than I did. Maybe you want to simplify that first and then pull this, the 2/5 out front, and then break it apart. I chose to do it in a different order. It really doesn't matter at this point. All right, so then this is going to end up being 2/5 sigma I equals 1 to 5. When I square this out, I get 4I over 25, and it's negative. So negative 4I squared over 25 plus, and then this is going to be, when I add up 5 times, that's that formula, the constant one, that this is just going to be 5 times 5, right? The first 5 because that's the constant, and then the second 5 because that's how many times it tells us to add it together. All right, now just for, because I want to be able to simplify this, and there's a negative, actually there's quite a bit of constant right here, so let me just distribute this 2/5 through to each of them. All right, so I've got 2/5 times the first one, which is going to be sigma I equals 1 to 5 of negative 4I squared over 25 plus, when I multiply 2/5 times 25, I just get 10. So plus 10. All right, so really all my work is going to come in here. And as I noted, that this negative 4/25 is a constant right here, which I can then pull out and join it with this. So this is going to end up being negative 8 over 125 times summation I equals 1 to 5 of I squared plus this 10. Sorry, my writing is so slanted right now. Okay, so then let's focus our attention on this. And again, if you look back to this sheet right here, we've got that formula for I squared, n times n plus 1 times 2n plus 1 over 6. All right, so I'm going to write this out. So this ends up being negative 8 over 125 times, I'm going to replace this with, again, let me just write this down over here just so you see where it's coming from. It's n times n plus 1 times 2n plus 1 over 6. And again, in our case, n is 5. So this is just going to end up being 5 times 5 plus 1, which is 6, times 2 times 5 plus 1, which is 11, over 6. All right, so I replaced this, whoops, with the version of this that substitutes 5 in. So here we've got 5 times 6 times 11 all over 6, and then I still have this plus 10. All right, let me clean up here. These 6's can cancel. This 5 can cancel out with one of the 5's down here, so we end up with 25 again. So we end up with negative 88 over 25 plus 10. I'm going to have to use my phone for my calculator here. When I do negative 88, oops, 88 divided by 25 gives me 3.52, so this is negative 3.52. And then plus 10. Oops, I'm not going to do that here. All right, plus 10. And when we do that, we end up with 10 minus 3.52. Phew, I get the right thing, which is 6.48. All right, so the underestimate, again, all that work that we're going to do, I'm just going to say, you know, dot, dot, dot. We did all this work, and we end up with 162 over 25, which is the same thing as 6.48. right? So it equals 162 over 25, and that gives us 6.48. So we can conclude that the area under the curve is greater than 6.48. Again, it's greater than because we didn't count all these little shaded in slivers. We just counted in this gray part, right? And so whatever the true area is, it's going to be greater than 6.48. I know we still have part B to do, but I want to be respectful of your time, so I'm going to stop right here. I know this is going to seem agonizing that you have to wait to see what happens on the second half, but I think it'll probably be better if you can start off fresh. So the next video that you look at will talk about how to do the second part. Okay, bye.